Hi everyone, my name is Yan. Today I'm excited to present our paper Black Box Membership Inference Attack against Fine-tuned Diffusion Model. Sorry. Nowadays, diffusion model can generate photographic quality image. And in the mid column, we can see with such generation ability, diffusion model can also serve as game engine to build video games. And at the current step, diffusion model can base on the current content to generate the next frame of the video game. And the primary reason diffusion model have such generative capability is still their massive training datasets. According to Stability AI, our official technical report, Stable Diffusion 3 was pre-trained with 1 billion image and fine-tuned with over 30 million image. With such amount of high-quality image used for training, as a researcher focused on AI security and privacy, I'm curious about whether this process includes data privacy problem. For example, the copyright problem. And to answer this question, a straightforward method is to use membership inference attack. So, okay, sorry. Okay, so in this page, I'm going to talk about how to use membership inference attack against image generator. It's similar with traditional membership inference attack against machine learning model. The attacker job is to infer the membership of the curated data. During the attack process, the attacker will feed curated data to the target model and can get the output, which we call it replicate image. And based on the information it got, it need to decide the curated data belongs to the member set or it belongs to the non-member set. And based on their different accessibility to the target model, we categorize the current solutions into 3 groups. And the first type of attack, we call it white box attack. In the white box attack, it means the attacker can fully access to the target model, include the loss value or even the internal gradient data. Because in the white box attack, the attacker can get too much information, so usually we think the white box attack is the most powerful attack. However, the drawback of the white box attack is impractical to use it in the real world, because in the real world, it's really hard for attacker to get the internal data from the target model. Also, the computation cost for the white box attack is really high. For example, some white box attack target diffusion model, you need to calculate the loss value at each denoising step. And diffusion model may have 1,000 steps, so to infer one query sample's membership, you need to calculate the loss value for 1,000 times. And the second type of attack, we call it black box attack, and we think it's the most realistic scenario. And in our work, we want to focus on the black box attack. In this type of attack, the attacker can only access to the replicate image, which is the model output from the target model. It cannot get any information from the target model. But with such limited information, the black box attack usually is the most hardest attack. And also some solutions said they are black box attack, but during the attack process, they still can get some information from the target model. For example, if the target model is a diffusion model, this attack said they can get the intermediate output, which is a denoising sample at each denoising step, and to use this data as the attack feature to execute the attack. And drawback of the gray box attack is same with the white box attack. It's really hard to use it in the real world because there are a lot of API-based image generative applications. So users just upload their prompt to a remote model and can only get the final output from the API, from the target model. So it's really hard for the attacker to get any intermediate output from the target model. And now I want to talk about 2 traditional black box attacks against image generator. And in this page, I just briefly talk about this. If you want to know more details about this work, please refer to their paper. The first attack is called Monte Carlo attack. And in this attack, the attacker first needs to sample a large number of replicate images. this point means the replicate image. And given a predefined radius r, the attacker needs to calculate how many samples within this arrow. The more samples in this arrow, the high probability this query sample belongs to the member set. And another attack is called gun leaks. In the gun leaks, the attacker still needs to sample a large number of replicate image at first. This is the replicate image. And then you need to calculate the average of the distance between each query sample, between each replicate image with the query sample. And the smaller distance you have, the higher probability these query samples belong to the member set. However, the drawback of these two attacks is all need to sample a large amount of data. In their paper, they said you need to sample 100,000 samples to achieve the best attack performance. And they are designed for the one-step generator, GANs and VAEs. But now we want to target diffusion model. And diffusion model is a multi-step generator. So if we sample 100,000 samples from the diffusion model, the computation cost will be really high. In our work, we want to improve this attack. So firstly, we rethink the threat model settings for the previous attack. In some solutions, in some paper, they said due to the consider of time-consuming and computing resource limitation, they directly use target model training sets as a member set. And for the same reasons, they don't use shadow model technique. But we think in some scenario, it might be hard for attacker to assess target model training set. And also, the attack with shadow model technique is more general because in the real world, we cannot directly use data from the target model to train the attack model. And also, some attacks are designed for the unconditional diffusion model. But now, the SOTA diffusion model is stable diffusion, which is a conditional diffusion model. And the model property has changed, so we think we need to redesign this method. And in our work, we aim to overcome this key challenge and design new methods to target fine-tuning phase conditional diffusion model. A finding in our research project is the selection of the attack feature is critical to the success of membership inference attack. In our work, we are the first to utilize objective function of the diffusion model to guide feature selection. Based on this idea, the likelihood of the query sample belongs to the member set can be quantified by examining the distance for a small set of replicate image with the query sample itself. And the idea is quite natural. The smaller distance you have, the higher probability this query sample belongs to the member set. And if you want to know more details about our theorem, please refer to our paper. And our attack pipeline includes 3 steps, and I will introduce them one by one. So here is the first step of our attack pipeline. We will synthesize the replicate samples. We'll have a query point, and we'll feed this query point to the target model for m times. And then we can get replicate image. And the query point usually have 2 components, text components and image components. For the query point without text components, we'll use image captioning model to generate one based on the image part. After we got replicate image, we then will use an image encoder to get image embedding from the replicate image and the query image. Then we will calculate the similarity score between each replicate image embedding with query image embedding. Then we can get similarity score vectors, and we will apply statistical function to get the proceed score vector, and we'll feed these proceed score vectors to the attack model. In our attack, we consider 3 different types of attack model. There are threshold-based attack model, distribution-based attack model, and cluster-based attack model. And the attack model is all trained with data from the shadow model. Now I want to talk about the evaluation setup about our work. In our work, the target model is stable diffusion with 1.5, and we use 3 datasets to test our attack. In our evaluation section, we use 3 different evaluation metrics to show the performance of our attack. And we compare our attack with 2 baseline methods. Like I said in the previous slides, we will train our attack model with data from the shadow model. And the shadow model is trained with the ancillary datasets. So at each direction, we consider the ancillary dataset setting. The ancillary datasets may have overlap with a target model training set, or does not have the overlap with a target model training set. And this direction, like I said in the step 1, the query point will have 2 components. If the query point have the text component within is this scenario, and if the query point does not have text component within is this scenario. So our attack consists of 4 different attack scenarios, and we have construct 4 attack. In the following table, we compare our method with the baseline method. We can see when the experiment setting is same, our method can outperform the baseline method. And we also did ablation study in our work. If you are interested to more details about our about this part, please refer to our paper. Then we did a case study. We want to use our attack as an auditing tool to target model on Civet AI. And here is an overview of the Civet AI. It's just a website that user can upload their fine-tuning checkpoint. And this fine-tuning checkpoint is trained with data belong to a specific art style or artist. And in our work, we download 7 checkpoints from the Civet AI. And in this page, I want to use the checkpoint trained with Qi Baishi paintings as an example. And the left-hand side painting is the original painting from Qi Baishi. And in our attack, we can consider it as a query sample. And in the middle one is the generated image, and we call it replicate image in our work, and it's generated from the download checkpoint. And we'll use it to compute the member similarity score. And the right-hand side is the generated image from the original model, and we will use it to calculate the non-member similarity score. And we want to quantify the difference between the member and non-member similarity score. So we build this table. We can say in this table, there's a clearly distinction between the member and non-member similarity score. And with this clearly distinction, we can say our method can serve as an effective auditing tool to evaluate the model on Civet AI. And now I want to make a conclusion. In our work, we first found that membership inference attack against one-step generator GANs and VAEs cannot be directly used to target multi-step generator diffusion model due to the difference in model architectures and generation process. So in our work, we designed an attack pipeline that can target conditional diffusion model, and we have considered 4 different attack scenarios, and we tested with 3 different types of attack model. We also evaluated key factors on the 3 datasets. If you want to know more details about our paper, you can scan this QR code. Thanks for your listening.
Any questions from the audience? Any questions? Okay. So
Yep.
I am just wondering about how big of a role overfitting will play in this setting, because to my understanding, the diffusion models, they're quite big, right?
Yeah. I think that's a really good question because, in my opinion, the foundation of membership inference attack is the memorization of the model. And in our evaluation section, we want to test it. So we fix the training step, and we test it with different fine-tuning steps. For example, the set with 100 samples and 200 samples and 500 samples. We can see because when we fix the training step, and the bigger fine-tuning set will maybe cause less memorization on the model. And we can see there a decline in the attack accuracy. So we think like Akil said in your question, the memorization is very important in our attack. Yeah.
Thank you. Any Other questions? If not, we're going to move to the next talk. Cool. All right. Thank you
Thank you.
for your amazing work.